Okay, I'm going to go ahead and I'm actually just going to fly through these slides relatively quickly. I'll be posting them online, but just there. These are the slides that the publisher put out there. They cover the bulk of it pretty well there. So, but then I'll get back to the problem I gave you the other day. And then I'm going to finish up with a little demonstration, which unfortunately I can't show it on the video because I can turn the camera on, but it's not very impressive looking here. But okay, this particular chapter, we're actually getting into the sum of products. We talked a lot about sum of products right there. And then Boolean algebra, I skipped over spending a lot of time on Boolean algebra. We'll see a few examples here, but Boolean algebra is going through the basic step-by-step trying to simplify our circuit by using algebraic methods that there. Everyone's had courses in college algebra at this point, right? That there. You know how very, some of it's very intuitive. In other words, you can see the answer quickly and easily. Sometimes you stare at it. That there. Boolean algebra is actually more of a that there. I have not used a lot of Boolean algebra, and you'll see why at the end of today's class. Why Boolean algebra it's kind of gone away. That there. The Karnoff map is probably the best tool. I gave you an example that I'll go through here after I collect everyone's work here and talk a little bit about that, where we can have a Karnoff map and get multiple right answers. One answer is not more correct than the other. Now, some answers will work, but they're not necessarily the simplest method. And we'll get into a little bit of more of the rules that I kind of skipped over when I went through the Karnoff maps the first time up there. I'm not going to spend a lot of time on exclusive ORs or NORs. That's it. Those are gates that they exist. They have a very useful use in parity checking. We'll talk a little bit about parity checking up there, but I'm not going to spend a lot of time on exclusive ORs. Get there. Then we're going to talk designing without a truth table up there, and then we're getting at the end of this chapter. We're talking a little bit about the electronics of these circuits. We have not. This is a course in electrical engineering. Everybody's in. And we haven't talked about any electronics yet, right? We haven't looked at any voltages, any currents, or any of those types of things. And we're going to look a little bit at that. I'm not going to get into the troubleshooting, and the reason is that troubleshooting is typically not something covered in great detail in an engineering program. You find that more in the technology programs. This particular book, I should point out, is written by three faculty in the electrical engineering technology programs, right there. Neil and Greg, they're at the Purdue West Lafayette campus. I was at the Purdue Fort Wayne campus, so I've known the two. We've known each other probably for close to 30 years. I think Greg started about the same time as I did. Neil's a little older than I am, so they've been around, and they've been teaching predominantly technology for the last 30 years. The campus I was at was a little different because we were a smaller campus, and when I first started there, we didn't have an electrical engineering program, so the regional electrical engineering program was the electrical technology program. So our program was more like an electrical engineering program. Later on, we started an electrical engineering program. I taught a few courses for that there, but I stayed with the technology program. So I'm familiar with both programs up there. Troubleshooting is typically things that technicians do more than technologists and engineers. There's some questions in people's minds that, which skill is more important for jobs in Malaysia? And that's a subject beyond this class, is whether they need more engineers or more technologists up there. Currently, the job market is more technology-oriented because it's more manufacturing. Manufacturing tends to hire more technology-type people. Design work is more engineering. So, again, that's it. I look for the job market to move more into the engineering field regionally. And it has to. The reason it has to move into engineering is because if you want high-value jobs with high salaries, you need high-value input, and that's the engineering work. Manufacturing tends to be much farther in the development chain, and the salaries tend to be much lower, and the returns tend to be much lower for the companies and the workers. So therefore, engineering is is going to become the mainstay. That's it. So, and then I'm going to talk about PLD devices, and I happen to brought one with. We're going to have a short little demo on it. I'm going to see if I can get enough of these to where we can do some labs using these. That's there. Unfortunately, as you look in this room, we don't have computers. That's there. I may try to steal another room, for at least the Tuesday so that we can get in there and do some labs. That's there. Otherwise, you're going to be doing demos. This is actually my own personal board that I shouldn't say I bought it. It was given to me by Altera a number of years back. That's there. And our students back in the U.S., each bought one of these individual boards individually. That was a requirement for the class, that they had to buy their own board. We've got some of the other boards that are a little bit larger than these here on campus. That they're, I'm going to try to, I don't know the word borrow, steal, beg, whatever, get my hands on them. That's there. So this board is actually very inexpensive. The ones that they have here are very expensive. I don't know why they bought the expensive one. I didn't write the check, so I don't know why they went that route. These boards, I think our students in the U.S. bought these for about 80 USD. So with the current exchange rate, that's close to about, I want to say about 350 RM, something like that. So they're not cheap, but the ones that they bought are the DE2s, which are a lot larger. This is much larger than you would ever use in a first year or second year course. That's where the DE0s, and they actually make one smaller. Hierarchical design method. We're going to get into my favorite topic. How do we design circuits? That's there. And that's going to be using software right there. So I have the software installed. I will make it available for you. The problem is I'm not sure if it's in all the labs, what labs it's in. Again, that's the problem. I need to find a computer lab that we can use for the rest of the course. Because we need to move into actually making you do some work. Me sitting up here talking is a waste of everybody's time unless you actually do some of the work. That's there. You have to do the work. That's there. And we'll get into HDL controls, if then else, that there. So, all right. We talked about this here, and I'm just going to kind of slide through this here. I apologize for Tuesday. I was fighting a little bit of a uncooked chicken in my stomach type problem. I don't know if anybody's ever eaten chicken where you see the blood after you finish eating it on the plate and you realize that you've just made a big mistake at there, which meant that you don't go much further, about 10 or 15 feet from the nearest restroom. That's there for the next 2 days. So that was what happened to me on Monday and Tuesday. And as a result, I also didn't sleep well. So that's there. But I'm back to normal. That's there. So let's talk a little bit about summer products. That's there. And what we've got when we look at a summer products here, and let's see if my pen works. Yep. We've got, this is a term, product term right here. This is called a product term right there. And that's A, and B, and C. This is another product term. This is A naught, B, C naught. Sometimes we would write this as term 7, and we would write this as term 2. In other words, we would write down what those terms are. And I did this the other day a little bit when I introduced the card-off map. I'm starting over again just simply because I want to make sure that I cover everything completely. Now, it's the case on a simplified circuit that not every term may have to show up in every expression, or every input variable doesn't have to show up in every term. Here we've got our terms A, B, C, D, and you notice that D doesn't, this term here doesn't have A, B, C. Here we don't have A, B. Here we don't have this one, we don't have C, D, this one here. If we simplify it, we'll see that those will drop out with the card-off map. That's it. Now, to be honest, I will show you kind of a drawing technique where I don't even bother to simplify it. I just put them all in just as they are. And I let the software simplify that. One of the beauties of today's software is that it does 90% of the circuit simplification for you. A lot of the work that you used to do as an engineer in simplifying circuits, we don't have to do anymore. We just stuff it into the software and bam, out comes the simplest design. That's it. Unfortunately, when the software doesn't work is when you have to understand what software is supposed to do. And that's why we make you suffer through this process. Is because, you know, once you go to working, you probably won't do it, but once every 2-3 years you'll have a problem, then you have to go back and you have to do it by hand. 90% of the time you'll let the software do the work for you. Same thing, I teach a course in microprocessors and I teach a course in microcontrollers. Actually, the microprocessor course, I'm using a microcontroller, but I'm teaching microprocessor. There I teach assembly language, and we get into the hierarchy of the device and everything else that's there. And then the second course, I jump in and I only use C programming, and I don't care what the inside of the chip looks like anymore. That's there. Because we let the compiler come up with the optimum code for us. We don't write it by hand in assembly language. That's there. Same thing with digital circuits. That's there. The software has gotten so good that we just tell the software what we want our circuit to do. It just spits out a circuit that works. And it works 99% of the time, right there. So these are all some of the products. Again, they're and terms that word together. At the end, this book doesn't cover it, but I'm going to add in, it'll probably be Monday or Tuesday, I will probably talk about a product of sums, where we would then turn right around and do the opposite of this, right there. And we still use a card-off map out there to do that. So, again, here we talk about product of sums. You know, he does this, he explains to it, but this chapter I didn't see, and of course I didn't read the book carefully. You're supposed to do that. I've read the book before. But we can design circuits using either sum of products or product of sums. Most students tend to feel more comfortable with sum of products than product of sums. They both show up in industry, right there. And the reason they both show up is because we talked a little bit. Let me slow down. I know I'm talking a little faster. We talked a little bit about universal use of NAND gates or NOR gates, right? If we're using NAND gate, we will use sum of products typically when we design. If we're using NOR gates, we'll use product of sums. And there's a reason why they come out that way. And I don't expect you to remember that. You'll see, it'll make sense when I do some examples why it works out that way. That's it. So those are the two terms right there. Here. And again, this is same discussion here. We're using, here's a very nasty looking circuit right here. This is our expression. By using Boolean algebra or Karnaugh maps, we can come up with something that is much simpler. Both these circuits will do the exact same thing. Now, back many, many years ago, and when I say many, many years ago, we're talking 35 years ago, before I went into this industry, a single NAND gate cost about $2. Now, it was quite expensive there, a single NAND gate. Now you can buy a single chip like this one here, the chip in the center of this here, and I'll go through this board here later, has about the equivalent of about 1.5 million chips on, or NAND gates on. It's very, very dense in terms of the number of chips on that there. And they cost maybe $8, US dollars. And, and please bear with me when I use US dollars for these prices. I do that for two reasons. One is that prices tend to be more stable in US dollars. If you follow the ringgit lately, you'll discover that the ringgit is low. I don't know what it is today, but the value of the ringgit changes daily, so I would have to change my prices in my mind every day. And they're normally priced by, this particular company is an Altera company, this name of the company. They're in San Jose, California, and they price everything in US dollars. That's the way they price. I happened to have been to their plant way back about 25 years ago. I visited Altera out there. So Altera was actually just bought by Intel, but out there. So we go through a process of converting this to that right there. Do you have a question there? Or okay. Sometimes when I see people that I'm not trying to embarrass you. I just want to make sure you don't have a question. I need to stop that. So we go through this here. And I'm not going to go through this example in great detail, but and I'm not going to put on the final exam anything where you have to use Boolean algebra to simplify anything relatively simple. But here we start off with this right here, and what you normally would do is you would take this expression right here and you would write that out, and you would go through it and multiply it. So if we did that, and this is probably do it on the slide, but I'm going to do it here anyway. Matter of fact, I have not tried this yet. Hopefully it works. Right there. Okay, there's my OneNote. Right here. Right there. And Z is equal to ABC plus AB naught AC naughted right there. Did I get that one right? There. Now the first thing we would do is we would apply De Morgan's theorem on this right here. Oh. Right here. And De Morgan's theorem, if you remember, said that AC naughted is equal to A naught plus C, right? Everyone remembered that? No. Be honest, nobody remembered that, right? That's it. But that's there. So when I see that there, A naught C naught naughted is equal to A plus C right there. Right there. So when I do that, then I'm going to turn right around and I'm going to multiply that out, and I'm going to say A B naught A plus C is equal to AA plus A B naught plus B naught C, right? Everyone see where I got that from? I just multiplied that out. Well, AA is what? A times A is A, correct? So this is A plus A B naught plus B naught C right there. Right there. And of course let me go back and correct up. And what did we do here right there? Don't. Right there. I wanted to previous page. Okay. Nope. Did I just say that I just put Windows 10 on here and I'm not sure how things were going to behave right there? Okay. And recent notes. And hopefully, this is, all right, let's start over again here. Right there. Okay. Right here, and I'm going to put it over there, and let's start all over again. Z is equal to ABC plus AB naught and if I can keep my fingers from touching the screen, right here, A naught, C naught, right there. Okay, so let's go through and let's just start this process again. This is all knotted. So we end up with Z is equal to, and give me a second here, I am going to cheat and right there. And the reason I'm cheating is so that I can write this better. A, B, C, or A, C naught. And then this is going to be A plus C, right? That's what I just did there right before. So I'm going through this step by step, right there. And this is a B, right there. I used to keep a little marker when I made 5 mistakes, class was over. That means I'm having a bad day. That's there. And students will diligently try to catch my mistakes so that they can go home early. But since we have very few meetings, you won't do that. So let's go through here and just let's just keep the ABC again, plus A A, excuse me here, let's get this right here. We're going to multiply this here. This is A, B naught A, plus or A, B naught C right there. Let's see if we got that right there. Yeah. I think I did it wrong the first time anyway. That's there. I have to multiply A, B naught A. So this A drops out right there. So we've simplified it some right there. So right now we're at A, B, C plus A, B naught plus A, B naught C. Now what I'm going to do is I'm going to combine these two right there. Right there. And when I combine these two, I get A, B, C plus A, B naught 1 plus C right there. I factored out a B naught for both these terms. So the 1 plus C drops out. Right there. So we're left with A, B, C plus A, B naught right there. Now we factor out the A right there. And we're left with A, and I'm going to say B naught plus BC right there. And that's that funky one that I never remember right there. Right there. And because that will reduce down. And let me go back to my previous slide. There, right there. Let me go back to my slides from chapter 3. Right there. And as you recall, there's a funky one here that we didn't really discuss much in great detail. Right there, as we go through these rules. Morgan's German's the one before that. Right. And maybe I don't find it right off. It's going back to our rules. Where's all our rules are? Actually, I think our rules are according to them. This is a case where I should have had the rules out in front of me. I'm trying to find that set of rules. And rule 17, D. Morgan's. All right, now we're close. This is the rule that I never remember right there. Okay. Everyone see this rule right here that we've got here. This is in this form right here. Right here. See this rule here? That's at 15b. Right there. And if you go back to my slides, let me put this back here to where here we look at 15b right here. Right here. This is the form B naught plus BC is equal to, if we look at that rule right there, as B naught plus C, right? So this is A, B naught plus C. That's our simplest form right there. Right there. That is our simplest form. So you can see all the steps we went through. That's there. I've been doing this a long time. I don't do it very often, but I remembered how to do it quickly enough because I've done it up there. Yeah, I'm not going to expect you to be able to do these kinds of problems up there. But this is what you would have to do if you were to do it manually. That's there. So let me go back down to my slides. And right there. And this is the slide we're looking at. And let's look to see whether they came up with the same thing. And they go through all the steps that I did right there. Now notice that they did do one thing here, funky, is that they show the double bar there. A double bar is the same thing, it's just the variable right there. I skipped the double bar, I skipped that step there. And they got to this point up there, and they all the way down here, and they ended up with AC plus B right there. Again, this is the same as AC plus B naught right there. And is that the same thing as what I had right there? Yeah. They end up with the same thing right there. I had it reversed, B naught plus C, but that there. So they went through the same steps. So as I said, I'll put these slides up online. Actually, I'm going to put the whole book up at one time. That's there, so you'll have access to all the slides I'm talking about. There. I don't mind doing that because if I just put the slides up and I read to them, then I'm wasting your time. That's there. So again, this goes through all the steps. That's there. I didn't do that on Tuesday, and I'm not going to spend a great deal of time requiring you to do it simply because this is the drawn out way of doing it. Right there. So this is the simplified circuit right there. Right there. All right, to solve any design problems. Typically, this goes back to my discussion of starting with a truth table. 99% of all design problems start with a truth table. Right there. So, again, this is looking at all the various possibilities of a two-input. You have 4 different possibilities here, and you can come up with there. I will show you a simpler way of how I do this using the Altera software later on. I don't know how long we have. So this is a problem here. Remember, we have a 1 here and a 1 here, so we have 2 AND right there. We have an inverter on A here, that goes to this right here. We don't have the inverter on B because it's 1, 0, and we have the inverter on B here. So we can easily do this very, very simple. That's it. And I can draw this very, very quickly using software. It looks almost like a PLA type, programmable logic array type software. Okay. This is, again, the same thing. We've got 3 1s. We have 3 terms in our output right there. Now, when we have the 3 terms in our output, we could go through and start using Boolean algebra to simplify that right there. So as we look at this right here, we can look at these first 2 terms. This is A naught BC plus A naught BC. I can factor out the BC and A naught plus, up there. Yeah, I did a mistake here. I got a mistake here. I factor out the BC. This is A naught. Oh, this is B naught right there. I would factor out the A naught B here. So this is A naught B right here. A naught B C naught plus C, and that drops out. So we could see that would drop out right there. So we could do that manually. The Karnoff map is the way to do this systematically right there. And so we would have A naught B plus A B C, and that doesn't look like it's good. I could factor a B out from there. That doesn't really save me much right there. This is equal to B A naught plus AC right there. And actually this would factor out then. That goes back to that other form that we had right there. So we could factor this out right there. So again, 3 inputs is only when the majority, that's here. So that's there. Now again, this is the way the problem is written here is a little tricky right there. The output is high only when the majority of inputs are high. So what you're looking for is two inputs that are high or more. So here's one, here's one, here's one, and what we're looking for is the number of ones right there. So just reading this problem is a little bit of a tricky one right there. Again, those are our four inputs right there. All right, I'm going to simplify the expression. I'll put only the majority inputs are high. Right there. This shows the circuit after factory. Right there. All right, now we get into the cutoff map. That's what I talked about the other day, and I'm going through it a second time. And I'm going to go through the slides that I didn't have the other day. And what we're doing here, and I would never use a Cardinals map for a two input. You can, but there's no need to. You can do that by inspection. That's it. So if we look at the 3-input NAND gate, 4-input variable, we skipped a 3. Where's our 3? Oh, I guess it skipped right there. That there theoretically can be used for any number of inputs. Practicality, it's limited to 5 or 6. I will not cover more than 4. It actually gets very messy once you get beyond 4. You can do 5 or 6 by hand. If you get more than 4, you almost always set a software. This is the 4-input that there. Notice here that this is the pattern that I used before. A dot B, A dot B, A B, that's there. Now I put little numbers in here. This is a 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Just simply to make it easier to remember, I just put the little numbers in there, right there. That way I just read across down. So 0, 1, 0, 0, 0, 0, and right there. And every place there's a 1, we put the 1 there. Every place there's a 0, we place a 0. And we can write the expression directly from the Cardinal map right there. This is the expression right there. Is that the simplest expression? No. That's there. And the adjacent K-map differs in only one variable, both horizontal and vertical. And remember that we loop around this way, this way, this way, this way, this way, all the various ways. And this shows a lot of the various combinations that we have. This is actually a series of groups of 2 right here. And this is groups of 4. This is a group of 8 right there. And we can have all kinds of various combinations. Now the rule is we have to circle every one at least one time. We don't have to draw every possible circle. As long as every one is circled at least once, we don't have to show that there. In other words, if we look at this one here, I could draw a circle, a pairing right there, right? Everyone see that pairing? I don't need to. The reason I don't need to is both these are covered here, and this one is covered here. So I could show this as 3 terms, but that would not be the simplest one. It takes a little bit of practice with this. So I don't have to show, for example, there's a group of 4, I don't have to show these 2 groups of 2. I don't need to do that. I show the largest groups that include every possible one output right there. When the largest groups have been looped, only the common terms are placed in the final expression. Loopings wrapped front, top, bottom, and sides. Right there. Loop ones that are not adjacent to any one. So you can have a group of 1 right there. Loop ones that are in pairs, in quads, octals right there. And this is actually a series of all kinds of instructions. It's practice, practice, practice right there. Okay, I'm going to skip the XOR here, and let's just go through that there. And let's just kind of go back and work more examples of the Cardinal map right there. I think this kind of wraps up all the discussions Karnoff maps here, and oh no, he does do more of that there. Oh, he talks about the exclusive OR. All right, let me go ahead and continue on and skip the discussion on the exclusive OR right there, right there. Up there. This is a circuit that the output is high if one or both outputs, if one or the other input is high. Up there. That's there. I'm going to skip that discussion for right now. Because it can be used for parity checking, and I'll come back to that there. And I thought we had some more going. Nope. All right. Okay, I guess I thought I saw that he was doing more. All right. Let's just jump out here and let's just do a couple more examples of the I want the care page. Yeah, evidently I don't have the little thing where I put the rule lines on. That's fine. Grid lines fine. I'm trying to get the thing where I can make this go away. All right. Well, evidently. All right. I guess we'll use it. Just go ahead and use it this way. All right. Let's just kind of go through, and I'm going to take this off where I can write on this as if it's a sheet of paper right here. And I'm going to basically say, let's just do a 3 input. A 3 input looks like this right here. Right here. C naught C, A naught B naught, A naught B, A B, and A B naught right there. So that's my basic Karnoff map right there for 3 input. If I put my numbers in 0, 1, 2, 3, 4, 5, 6, 7 right there. So let me write my function here, A, B, C. I'm going to show my output as X. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. See, it's actually, my handwriting is probably neater if I do it this way than trying to write this that way, right? That's it. Okay. So if I do that there, and I'm just going to put some random ones and zeros, just like I did the other day. Right there. Now, what I can do here is I can put over here our numbers, 0, 1, 2, 3, 4, 5, 6, 7, right there. And I'm trying to give you as many ways of cheating on the final exam as possible. Right there. Because if you put these numbers down, it reduces the probability of generating an error when I move it to the table. So the 1 has got a 1, the 2 has got a 1, the 5 has got a 1, the 6 has got a 1, and that's it. There's 1, 2, 3, 4. I got 4 ones, so this is 0, 0, 0, 0. Now, when I look at this right here, this is where things get a little tricky. Right here, is that I've got two groups of two right there. Here's a group of two right there, and here's a group of two right there. So I'm going to have two terms in my output. I have a term for every circle right there. And as I look from this, let's look at this circle here first. As I go from the top to the bottom, the A changes, right? So this one here is going to be right here, B not C right there. Because in this term here, this is A not B not C here. Down here is A B not C. The A changes from A not here in the top to A on the bottom. So the A drops out. The one that changes, you drop out. This one here, the A also changes. But this one here is B C naught right there. So my simplest expression is going to be B C naught or B naught C. So that would be the answer that I would look for right there. Now let that absorb for a few minutes up there. And let's just do it again. Right there. It doesn't hurt to do this multiple times, right? That's there. Multiple times, because you're going to be expected to do at least one of each of these. So that's it. So again, the same thing. Let me put my right there. I want to do my it just makes it easier if I put the rule lines on here. So the same thing, I'm going to do a 3 input. And again, I'm just going to do this at random. A and A, B, C, X. And I don't know why my lines are going this way here. Right there. 1, 2, 3, 4, 5, 6, 7. Okay. All right. This one here, I put a lot of ones there. And again, I'm just going to cheat and put my 0, 1, 2, 3, 4, 5, 6, 7 there. So now I draw my Karnoff map. And my lines are not very straight, but that's all right. They don't need to be straight. They also don't need to be equal. Here. Okay. All right. Now I'm going to do this a little simpler. Since I've only got 2 zeros, I'm going to write the zeros down and then put the ones in. So I've got a 0 and 2, and I've got a 0 and 5. Everything else is a 1. Right. Go ahead. I'm going to put this up there. Right there. So when I look at my groups here, now this one's a little trickier because that there, as I look here, I've got groups of, I don't have any groups of 8, right? There's no groups of 8. Do I have any groups of 4? No. I can't group these 4 together. I can't group the 4 corners together. I can't group either of these rows together. So it's only going to be groups of 2. So the trick is to find our groups of 2 that's going to cover everything. So now let me show all the possible groups of 2, and then we can look at the fact that we're going to not use all of them. So this is a group of 2 right there, right? This is a group of 2. 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 Right there. This is a group of 2. You see there's a lot of groups of 2 there. We're not going to use all those. We're going to pick and choose, and we want to pick the ones that, let me erase all my groups here. Here. And let's pick the groups of 2 that best suit our method. Now, again, there could be more than one right answer for this one. This is the tough one here. So I'm going to say that let's use this group of 2 here, this group of 2, and this group of 2. All right? We don't circle anything twice. So this is a good answer. Is this the only answer? No, it's not the only answer. And that's what makes these problems a little bit trickier, is the fact that they're, so, but this is a good answer. This answer right here is going to be, I'm just going to write the answer A naught, B naught, or B, C, or it looks like A, C naught, right there. So that's one answer. That's one answer. There's nothing wrong with that answer there. We can use that answer. That's it. And that didn't work too well. I want to circle everything here so that I can. Right there. There should be a thing where I can. All right. I want my keyboard. Where's my keyboard? Okay. Control C. All right. I changed my keyboard on me here. Control C. Yep, evidently that didn't work. All right. Let's just go back to the previous page. All right. Let's just use this page here and erase this and start. So everyone has this down. Since this is recorded, I'm going to erase this and start over again. Right there. I'm going to leave this answer there, but I'm going to erase these 3 circles here. Right there. I'm going to erase this circle here. Okay, so let's try doing a different group. Let's do this group here. do this group, and do this group right there. I got 3 groups there, right? The same. Every one is circled, right? So that's a right answer. So I could write this answer as the first one there is going to be, it looks like it's B naught, C naught, or A naught, C, or AB. Both answers are equally correct. So which one's right? They're both right. Right there, they're both right. See, and that's why sometimes when you look at these problems, it can be confusing. Which one? Here, I think the one I gave you the other day was like this, right? You had multiple correct answers. That's it. So, and this makes design problems unique from other types of problems is that here we're given a truth table right here, and I said design a circuit, the simplest circuit, and I come up with 2 different, and there may be a third correct answer. I'm not going to hunt for the third correct answer. But this is a situation where we have 2 answers that are equally correct right there. Now, the same thing happens if, say, you're designing an op-amp. Have you had a course in op-amps yet? Does anybody know what I mean by an operational amplifier? That there? Nope. That there. So if I wanted to say I wanted to design a voltage amplifier with a gain of 30, that there, it's a non-inverting amplifier, I could design 20 different amplifiers, all have a gain of 30, and all 3 will work. That there. Now sometimes you put other criteria on it. So that there. All right, let me just go through and now do another example with 4. I'm not going to go through a lot of these, but I think you've seen enough examples. I gave you one, and then I'm going to go back and finish up the chapter. So let's do a group of 4. And view. It helps a little bit to put the grid lines in there. So again, if we're going to do a group of 4, A, B, C, D. And here's where my handwriting gets where it's interesting. And I may shrink the page down to make it a little harder to read. The problem I run into is that the screen resolution is huge. That's it. Okay, and I'm going to okay. That's always nice when I get to 15. I go from 0 to 15. Means I didn't skip one right there. So now, at this point here, I'm just going to put in our 1s and 0s. Again, this is purely random right there. 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1. Okay. So there's my 1s and 0s right there. And draw my Karnoff map. And you can probably guess I never took a course, and I was very successful at with drawing right there. I actually was department chair for about 5 years of the interior design program at my previous campus. And I had multiple people that taught hand drawing and those types of things that worked for me back there. They were all great artists, and they all just kind of laughed at me back there. Of course, they didn't laugh at me when I pointed out that I was the one that selected who taught what schedule, so they laughed too much at me. You were teaching classes at 9 o'clock at night back there. I never did that to anybody, but yeah, got to threaten people once in a while, right? My wife will threaten me by forcing me to eat durian 3 days a week, but she knows that I would not eat durian. Right there. C naught. Putting that up. C naught. C naught D. C D. And C D naught. Right there. My numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, U, F. Now remember that you go down, you go 2 and skip 1, come back. Across, you go across 2 and skip 1, come back. Right there. So then I go through here, in every place there's a 1 in this table on the left. I put a 1 on the right-hand side of the table on the right. So 0 is a 1, 1 is a 0, 2 is a 1, 3 is a 1, 4 is a 0, 5 is a 1, 6 is a 1, 7 is a 1, 8 is a 0, 9 is a 0, A is a 0, B is a 1, C is a 1, D is a 0, E is a 0, and right here. So there's my table on the right-hand side. Now here, it's the same rules right here, and right there. Oh, I thought I could just. Okay. Right there. I'm going to try to make that as large as I can. Is that readable? Everyone can see what's going on there. And let me change colors to where we'll use pink. All right, there we go. So we got pink here that we're going to circle here. Now, we're looking for groups of 16. Now, a group of 16 means it's all ones, right? So we don't have a group of 16. You're rarely going to see a group of 16. Do we have a group of 8? It doesn't look like I have a group of 8 right here. So it looks like, do I have any groups of 4? Yes, right here's a group of 4, right? So here's a group of 4. Actually, that pink doesn't show up real well, but we'll go ahead and use it. So there's a group of 4. Do we have any other groups of 4? Yes, we do. This is a group of 4 right there. We have a group of 4 there. Now, we have this one here can't be combined with anything, right? So this is a group of 1. This one here can be combined with this right here. And this one here has to be combined with that there. So this is a messy one. This has got a lot of groups in that there. And I see no way of making it easier. That there. We have here, when we look at this here, we've got 2 groups of 4 and 2 groups of 2 and 1 group of 1. So we got 2 4s, right? Right there. This is a group of 4 right here, and this is a group of 4. We've got a group of 2 here, and we've got a group of 2 here. So we've got 2 2s right there, and 1 group of 1 right there. So that tells me we're going to have 5 terms in our output right there. So as we go through this here with 5 terms, we'll write the groups of 4 first. A group of 4 is fairly easy because 2 terms drop out. So the first one, and I'm going to show this group of 4 right there first. So if we go with that one there, right there, that group of 4 there, everything on the top is A naught, and everything to the right is C, right? So this first group of 4 is A naught C. Now I'm going to go back and I'm going to select another group of 4. I'm going to try to find a different color here. This group of 4 right here. Now a group of 4 on a row is easy, or a column, because I just read the top of the row, or the column in this case. So this is CD right there. So those are my 2 groups of 2, or 4, excuse me. Now we've got to look at our 2 groups of 2. We've got 2 of those right there, and one of them is this one right here. Oh, that purple is horrible, isn't it? We won't use purple. We'll use light blue there. Okay, right there. Actually, as you can guess, purple is my color. Yeah, that's there. As my keyboard is purple and my mouse that's there. But we won't use purple for a highlighter. Okay, so as we look at this group of 2, only one term drops out, right? So as we go from here to here, what changes? C. So plus, so it's A naught, B, and D right there. So that's that one group of 2. Now we got to do the next group of 2. And our next group of 2, let's see if we can find a color that, and we'll use blue again. Right here, this group of 2 right there. That's there. In that particular case, D is changing, right? This term here is A naught, B naught, C naught, D naught, right? This term here is A naught, B naught, C, D naught. So C changes. So C drops out. So it's going to be A naught, B naught, D naught, right? Is that okay? So then there's our 2. And then we have to do our final group of 1. A group of 1 is easy because you just write down what it is. A, B, C naught, D naught, right there. So this is the solution to this particular problem. This is as hard as you'll see on any test that we'll do. This is as hard. If you could do this, you're okay for this part right now. That's it. So with that said, I'm going to stop this here. I'm going to spend a few minutes. Normally I stop after about an hour, but I'm going to spend a little bit longer today. One is to make up for the fact that Tuesday I shortchanged you a little bit. And I've got a couple of topics I want to talk about. That's it. Okay. Let me close this one here. That's it. And actually what I'm going to do here, let me put my keyboard on here. Right there. And let me take this off. I don't need this anymore. What I want to demonstrate to you here, and I'll talk about it with the slides later on. We'll come back to it. But this, well, yeah, let me just bring the slides up here, kind of up there. This is the current slide right here. Okay. All right. I'm going to jump here. We'll come back to the slides. This right here is called a PLCC, or Programmable Complex Logic Array. It's actually a CPLD is what it's called, a Complex Programmable Logic Device right there. It happens to be an EPF up. And where are we at here? I got totally lost on my slides. Yeah, okay, right here. And if you were to look at this board right here, and I'm not going to pass this around at this point. The plan is for you to have time to play with these yourself. That's there. But this chip here is this company, this is like Altera, this is like Cyclone part. This particular slide happens to be a 7000 Max series, which is an older device. It's the one I used to use up to about 3-4 years ago. But I actually designed the board to use with the Max device. So I'm very familiar with the Max device. That's the 7000 series. I didn't bring any of those boards with me. I probably should have. Up there. But this one here, I quit building my own boards because I couldn't build them cheap enough to compete with the guys in Taiwan. The boards I built were a lot larger and a lot more had a lot more on them. It cost twice as much as this board does. So I quit making my own board. I started buying them from Taiwan simply because they're cheaper right there. So this is from a company called Terasic. I've been got there. This is a complex device. This happens to have inside of it all the digital logic that you could ever possibly want for this class right there. So we designed with this using software package right there, and they go through some of this other stuff. I'm going to not go through this now. We'll come back to these slides here. Right here. I've got installed on here, and okay, I guess I have to find it in here. Okay, the software that we use here, and I don't know how easy this is going to be to see on this board here, right here, but this is the software that we're going to be using. I think I did a quick demo on this before, but I'm going to go through it a little bit more detailed right there. I did a short little demo. This board just plugs into, and we don't care about that. This board just plugs into a USB port. You don't need any power supply for it. And it comes up, looks just like this right here. Lots of blinky lights, right? Up there. Lots of blinky lights. We've got 10 switches on the bottom here. We've got 10 LEDs across here. And we've got 4 7-segment displays. That's there. It also has got, a VGA output, a mouse input. It's got a card reader. It's got all kinds of things, outputs that we can put out to the outside world. Obviously, this is a first semester course. We're not going to use a lot of it for it. That's it. But what we can do with this board here is I drew this beforehand. This is a relatively simple circuit right here, right there. And I realize that that's not easy to read there because our resolution's not good. But what I've got here is this is just simply A naught B plus CD is all this is right there. Just a very simple function right there. If I here now I've assigned some pins on this right here, and let me kind of go through. This is the manual, and I'll get the manual. I'm not going to post the manual up yet. The reason I'm not going to post the manual up yet is because my suspicion is that we'll be using the DE2s, which is the larger board right there. If not, I've got one of the DE0s, one of the DE2s, and we'll have to kind of share the board if I can't get my hands on others. But this is what the board looks like right here. That's there. And we can see, that's what it looks like in a little bit more detail. You can see this is the chip we're programming on right here. Everything else on the chip we're not interested on this board. We're not interested this semester. This happens to be, if we look at it here, we've got some flash memory. If we wanted to add memory to it, if we wanted to stick a microprocessor in this chip, we have some memory to it. We've got some static RAM there to it. That's there, dynamic RAM. We've got the 7-segment displays. We've got the program, and we'll talk a little bit more about that. We actually have an LCD interface that we can plug into this board. It would just solder to right here on the board right there. You would solder an LED if you wanted an LED on this board right there. It doesn't come with the LED right there. It has a separate power supply input, or you can use it through the JTAG. It also has its PS2 port, SD card reader, a VGA, all types of various connectors. So this is the board we're looking at right here. Now, as we go through this board, right here, and this is the manual for it, right there. In the manual, they show us here, there's my 10 switches there. And they show that switch 3 is on G4, H6, H5, and H6. So when I design the circuit, I can tell it what pins to put this onto so that I can put that there. On the next page, right here, this shows me that here's my LEDs. I've got 10 green LEDs right there. They're actually, yeah, they are green LEDs right there. So this also shows me, gives my pin out that there. And I've got some push buttons there that I can use. So I've got all my inputs and my outputs specified on the board. So I don't, I'm only using these switches and these LEDs for right now. And those are tied directly to this chip right here. So when I build my circuit right here, I have an option here of edit assignments. Here we go. And we've got our pins. And you can see that I went through before class and I assigned my pins to those switches right there. And I can change them whatever. In other words, if I go back to my circuit right here, and if I say I wanted to use, instead of LED there, I just change that to J2. So I would just change this to J2. J2, and it would use the other output. So this is how I assign my pins to this here. So once I've done this, I can go through here. I can compile this circuit. This takes forever, by the way. But it's a very slow process because it does all kinds of stuff in the background. It optimizes the circuit. It does all kinds of things in the background. We're not going to worry about that today, what's going on in the background. It's giving me some warnings. The warnings are because I don't have the right timing information. And I don't have any clocks back there. This is a relatively simple circuit. So it gave me some warnings. I can look and see what the warnings are. No clocks defined. No clocks defined. Constraints are not found. No clocks in design. That's there. No clocks designed. Some pins have complete idle. That's there. So I'm ignoring the warnings. I can simulate what the output looks like. Right here. Now I did the simulation beforehand so that right here, and we can see there's my outputs A, B, C, and here's what my outputs look like right here. Right there. This is what my output should look like right here. And I didn't verify it, but that's what my outputs look like right there. So I can see what it's going to look like. Now the next thing I could do is I can then program this board and start. And now that design that I did is now inside this board. So now I can start flipping these switches right here. And you'll probably see if I turn them all off, it's off. If I turn on 1 and 2, this LED comes on. So in other words, it's matching what I'm seeing right here. So if I turn those two off right there, and I turn on, say, for example, 1011, 1011, the LED comes on. So I'm actually seeing the design that I built in the schematic show up on my board right there. So this is the way we typically do digital logic today. The old way would be to hook up the chips and wire the pins. Now we do it internally. If we were to look at what's going on inside this, where's our spitter? I'm going to flow setting. Let's turn off the simulator right here. Compilation fitter. Now, as we look at this particular one right here, we can see that I'm using less than 1% of the chip. That's there. This particular part has 15,000 logic elements. I'm using less than 1. Right there. So now this particular chip will do a lot right there. I'm using, out of 347 pins, I'm using 5. 4 inputs and 1 output there. So I'm using 5 pins. Memory, I'm using 0% of the memory. Using the multipliers, I'm using 0%. The phase lock loops, I'm using 0%. So I'm using very little of the actual IC. So, but this is the way that I typically will will work with the labs. I'm going to try to get my hands on at least how many people we've got. I didn't count how many people. We've got about 20 people in here. So I want to get at least my hands on about 5 of these groups of 4. They're right. But we'll see how many he's got. I've got 2. The problem is I got 2 different ones, and I know that he's got a different one yet. So we may have multiple types. Now, multiple types is no problem, except for when we look at these pins, they're all different. Right there. So if we have multiple types, we may have to go through and assign the pins. I mean, the circuits will be the same, but where you assign the pins are going to be different. And the other thing that changes a little bit is when we do our project settings, right there. Right there. See, this number right here goes to the chip number on the board. Right there. So if we have a different board, we would have to use the compiler settings. Everything else is the same. But this is really where I'm looking at moving, because especially when we start doing things with flip-flops and clocks, it's a lot easier to work with these boards than it is to work with ICs on a board. So I just kind of wanted to point that out. This is kind of a demo. I think I showed the software before, didn't I? I remember showing a short little simulation, but this was the first time I know it's the first time I showed the board, because I brought the board with me. It was in my filing cabinet, but I had to go find a cable for it. So I know I didn't turn on this board until this morning. So I know that I didn't show the board before. That's there. But that's there. Like I said, I've got 2 of these. I wish I would have brought more of them. That's there. Any questions on where we're at? Now, everyone's owes me a sheet of paper, right? That's there. So pass those on up. Up there. I said I was going to collect it before class, but up there. But I did say I wanted you to turn in that one, right? Or did I ask you to turn that one in yet? No? I'll let you slide if you say I didn't ask you, because I don't remember whether I asked you to turn that in. I gave you an assignment to do, right? I don't know if I said it was going to be turned in. Did I? No? Okay. I'll let you slide, but you'll see one coming up. Back there. So, all right. Any questions? Back there. This is probably the longest I've talked for a class. 1 hour, 18 minutes. I'm still under. It's my 2-hour allocated. Do you have instructors actually talk for 2 hours? What do they do for 2 hours?